Hi class, today we're going to be covering two different sections, 7.10 and 7.11, the kinetic molecular theory of gases, also the movement of gas particles. So the first thing we're going to start off with is the kinetic molecular theory of gases, also known as the kinetic theory, the theory of moving molecules. If I refer to it something to that extent, just know I'm talking about this. Okay, so the first thing you need to understand is the ideal gas equation describes how gases behave, but not why they behave the way they do. These 5 postulates are going to help explain that. So the first one, gases are composed of small molecules that are, in constant random motion. These molecules travel in a straight line. Unless a collision occurs, they will bounce off each other and change direction. Think of pool balls on a pool table. If they're very quickly, they will bounce off and just go in a different direction. Number 2, volume taken up by the molecules themselves is insignificant compared with the overall volume occupied by the gas. What this means simply is gas is mostly empty space. It's completely different than solids and liquids, which are non-compressible. Have you ever tried to press down on something that's solid like a countertop? You can't do it, because all the particles are so close together to each other. There's little to no empty space, where in this case, the gas molecules are very spread apart, depending on the conditions. Number 3, forces between molecules are negligible. What this means is a molecule will continue moving in a straight line with an undiminished speed until it collides with another gas molecule. So gas molecule, the pressure that exists from the gas molecules is that's being exerted when the particles hit the sides of the container. The collisions transfer energy. Number 4, we assume that the particles do not interact with each other. No loss of kinetic energy, which is kinetic energy is energy of motion. They simply bounce off one another. So think about 2 steel balls. I don't know what they call that thing that you hit the balls and they just keep bouncing off of each other. They just bounce off. No energy's lost. They go on with their business. And number 5, the average kinetic energy of gas molecules is proportional to the absolute temperature of the gas. When you read the word absolute, that means Kelvin. That's what we're talking about. And basically, if the temperature of the gas goes up, then the kinetic energy of the gas also goes up. Here is just a breakdown of everything that I stated. Postulate 1, gases consist of particles in constant motion. Postulate 2, gases are mostly empty space. 3, particles exert pressure when colliding with the container, which is a picture you see here. This is mass times velocity. The pressure that arises is from the molecules colliding with the walls of the container and not with collisions between themselves. Postulate 4, particles do not interact. There's no intermolecular forces, which means there's no attraction or repulsion. They just go on with their business. And molecular speed is proportional to temperature. Okay, so distribution of molecular speed. A gas is in constant motion. Sample of gas, the gas that has an average kinetic energy is an average speed. The individual molecules of the gas are moving at different speeds. So what basically I'm saying is that there's an average kinetic energy, which is the average speed of the gas, the sample of gas. But in that sample, each individual molecule, they're moving at different speeds, but you take the average of it. So at any instant, the molecules in a sample have a wide range of speeds. Why is this? Because each molecule collides frequently with other molecules, and they might be deflected off at a high speed while another is nearly stopped. This leads to a wide range of speeds. So this is kind of like a bell curve where you have a bunch of different ranges here and a bunch of different ranges here, and then you take the average of that, which is the average kinetic energy that we're interested in. Also, the higher the temp of the gas, the faster the gas particles move. So if we look here, we have number of molecules and we have speed. At 25 degrees Celsius, we have oxygen that's pretty much all of the molecules are all the molecules are in this little curve. But there are different speeds even within this. But as the temperature increases, that will also increase the average kinetic energy, and then you'll have an even wider range of molecules all going at different speeds. You can still determine what the average is, kinetic energy, but you'll have a wider range as the temperature increases. Okay, which takes us to root mean square. It's a U with an RMS, speed, and molecular mass. What this is this is the speed of a molecule possessing a kinetic energy identical to the average kinetic energy of the sample. So, and it is related to the mass. If we take a look here, you can see, again, there's molecules, and this is speed. What you see is that oxygen is over here, and hydrogen is over here, and helium's here. This has to do with the mass of these gases. The heavier gases will not move, will not have the same speed as the gases that are lighter in mass, which is helium and hydrogen. So there's a wider range of speeds going with the helium and hydrogen compared to the heavier gases, which the molecular masses of these gases are not, considerable to what we look at for other elements. But for gases, they're heavier, so they're not going to move with the same speed as the lighter gases. And this is the equation that we would use. So this is the square root, and underneath the square root is a 3. R, gas constant, which I'll show you, and then the temperature and the molar mass. We use the 3, 2. If there's a 2 here, that is to determine the most probable speed of a gas molecule, but we're not interested in that. We want to know what a molecule is matching the average kinetic energy of a sample of a gas. So here is a problem. Let me break this down because we've been using a gas constant for the ideal gas law, but this is a little different than that. So calculate the root mean square speed of carbon monoxide gas. I don't think carbon monoxide's on here. No, it's not. Okay, so I need to break this down at 25 degrees Celsius and 100 degrees Celsius. So there's going to be 2 equations, and we're going to see what the average kinetic energy speed of this is. Now, first thing, this units, the final answer should be in meters squared. So we have to use a different gas constant in order to get there. So molar mass for carbon monoxide is here. We are using kelvins, so we're going to change the Celsius to kelvins. And then we're going to use a different gas constant. Why? Because we can use something to get to different units that we want. So we're going to use R is 8.314 joules per mole per Kelvin. But 1 joule equals kilograms meter squared second squared. The most recent place that we used this was in chapter 6.1 to be exact. We'll cover this. So if you're not familiar with what this is, go back to 6.1. It's even earlier in the book, but the most recent place was 6.1. Now, by doing this, we can exchange, we can move out the joules for the kilograms meter squared second squared. And with that, we can cancel some of these out, and that will leave us with meters second squared. So here is the first problem. I bold-faced it. So we're just going to plug everything in. So the 3 is there. And then we have R as the gas constant. Make sure you have all the units that go with this, because that's how you're going to know if you did it right, by canceling out the units. Then we have our Kelvin. We have our molar gas, but the molar mass, the molar mass of our gas has to be in kilograms in order to cancel this out. So make sure that if you're using grams, you have to also use the conversion to get it to this canceling out. This is a problem that has a lot of units. So if you're not doing it right, the units aren't going to cancel out. That'll be your first indication that something's not right. So with this gives us an answer of 515.3 meters per second. And I told you these units have to be in meters per second, and it is. So now let's compare the speed at 100 degrees Celsius. So here we plug it in again, and the only difference is the temperature, because we're using the same unit, the gas constant. We're using the same molar mass because it is the same gas. We are converting it to kilograms, and we end up with 576.5 meters per second. So at a higher temperature, the average kinetic speed is faster, which is exactly, it's moving at it, and it has increased, which goes with postulate 5. Molecular speed is proportional to temperature. As the temperature rises, that means that the average kinetic energy will also, the molecular speed will go up. Make it easier if I say molecular speed. Okay, so now we're going to get to gas diffusion. So gas diffusion. Diffusion is the spread of one substance throughout a space of a second substance. So a gas sample is introduced into a larger volume. Gas particles spread out to occupy the entire volume, mixing with the other gases present. This is very easy to understand. Think about somebody walking in with perfume on in a big room. That smell of that perfume or cologne will eventually reach your nose if it's strong enough. And that's exactly what this is. It's being spread out into a larger volume, so it's mixing with the gas that's already existing, which is what we breathe. So that's what you see if this starts up again. Let me see if I can change the page, because that usually starts it again. And you see how it's separated, and now it will diffuse into each other. And eventually, you'll smell the perfume. Excuse me, all of a sudden my throat starts acting up again. And you can see the path traveled is not a straight line. Even though we said it's a straight line, it depends on the collisions, and that will alter the direction of the molecule. And a lighter gas will diffuse, so a lighter gas means a lighter molar mass, will diffuse quicker through a space than a heavier gas. And just look at the molar masses to determine, you can have an idea based on that. So here is, I found this nice little GIF that looks like what would a particle be trying to interact and go through, and it's just crazy little path here. I'll get my arrow out of the way. So gas molecules travel in a straight line only until they collide with the container wall or another gas molecule. The rate depends on temp, mass of particle, and collision with other particles, because that does alter the directions. You can just stare at this weird little GIF I found, and it's kind of it's interesting to watch. So also I found these pictures online. This is, I don't remember the gas now. I think it's, I don't remember the gas. A halogen. It's probably, I don't want to say it's bromine right off without confirming it, but I cannot remember because bromine is a solid. Okay, let's just pretend I don't remember. I don't know the name of the gas and forget what I said. But here's a gas. And I put this together and now lost my notes on this. And as you can see, it's dark. And it starts going through, it will start to fuse. This is after 4 minutes. You can see that this is not as clear as it was here. And then after 11 minutes, it looks pretty even on both sides. So even at the 4 minutes, you can see it's still darker here. But after 11 minutes, it's completely, the gases have diffused with each other. And the mean free path is the average distance traveled by a molecule between collisions. And as you can see, as you can see here, it gets kind of hectic. Sorry, I had to pause to clear my throat. Also, what affects the mean free path is high pressure. More particles per unit volume. So there's more collisions more likely to occur, and that will reduce the mean free path. So here's something I found online. It is ammonia and HCl. And there's cotton balls, and they're put in this tube. And what will happen is that the vapors will interact. Now, ammonia is a lighter, has a lighter molar mass than HCl. So the vapors from this will travel farther. It will diffuse quicker than the HCl. And what happens is that when they meet, you can see it meets closer to the HCl side than the ammonia side. And that is because of the gas being lighter, the ammonia being lighter molar mass than HCl. And it forms ammonium chloride. So that's what this white mist that you see in here is. So now we cover effusion. So effusion is escape of gas molecules through a tiny hole into an evacuated space. But this has nothing to do with collisions. So this is the difference with diffusion. But we will use the same equation, which will be on the next page, for both diffusion and effusion. Effusion is different in nature, but the rate of effusion of a gas follows the same form as Graham's law. So we're going to cover this on the next page. So basically, diffusion and effusion, they're only different because one will come out of a tiny hole, the other will be in a large volume that will mix with another gas. But they're just different ways of describing gas movement. So here is Graham's law, and this is another equation we're going to cover. So Graham's law relates the molar mass of two gases to the rate of speed of travel. Basically, I've already discussed that the gas that is heavier will not travel as fast as a lighter gas. And we want to know the ratio of these two gases set up to each other. So the lighter gas will always have a faster speed. So we expect that, but by how much? So it'll give us a numerical value. Here we have R1. That is the rate of effusion for gas 1. And that should be the lighter gas. The molar mass, calculate the molar mass of the lighter gas. That should be up here. R2 should be the heavier gas. And then what happens is that they are placed inversely to each other. So M2 should end up with the gas that has the heavier molar mass, and M1 should have the lighter molar mass on the bottom. So here's a problem that I did. Calculate the ratio of infusion rates of molecules of carbon dioxide and sulfur dioxide from the same container and at the same temperature and pressure. So here I wrote everything out. So R1 is CO2. Why is R1? Because the molar mass of CO2 is lighter than the molar mass of R2. So then I put it M1. So I know that CO2 is going to be here, SO2 is going to be here, and then I remember I have to flip them. The heavier gas molar mass should be on top. The lighter gas should be here, molar mass, and that's exactly what I did. And it gives me a ratio of 1.21, and this would really be over 1. So what that means is that CO2 effuses 1.21 times faster than SO2. And I put in parentheses here to make it even a little bit, hopefully, easier to understand. CO2 molecules move 1.2 times faster on average than SO2 molecules. So this is a ratio. We're setting up a ratio to determine how much faster the lighter gas moves on average compared to the heavier gas molecules. And this works for diffusion and effusion. And that's it. Thank you.